Okay, so let's continue for our revision of the chapter heat transfer. So let's begin with question number 1. Okay, so describe the mechanism of heat conduction in a non-metallic solid. So non-metallic solid, it means the insulator. So insulator consists of only one way of heat conduction, which is the vibration of the lattice atoms. So what we need to do is list out the mechanism of the heat conduction of the vibration of lattice atoms. Okay, so firstly, when the heat is supplied to one end of the metal, so the energy gained by the lattice atoms increase, sorry, and and um and the lattice atoms begin to vibrate vigorously with larger amplitudes. So this is the first statement that we discussed from the previous video. So the energy gained by the lattice atoms causes them to begin to vibrate more vigorously with larger amplitudes. So after the vibration, the vibration of the lattice atoms causes them to collide with the neighboring atoms. So the vibration of lattice atoms basically causes them to collide with the neighboring atoms. So the collision cause the heat energy to be transferred. Hence, I can conclude that, okay, so this is hence. So hence, I conclude that the heat conduction, so let me, okay, oops. So let me just drag it down. So heat conduction is actually occurs. So this basically is the mechanism of heat conduction through the vibration of lattice atoms, which is occur in both metals and non-metals. But the question is required for the non-metallic solid, which is insulator. So the insulator only consists of one way to conduct heat, which is the vibration of lattice atoms. Alright, so this is the first question of part A. So let's just move on to part B. So, okay, this is still number 1. And part B, number 1. So define the thermal conductivity of the materials. So we know that our dq over dt is actually equals to negative thermal conductivity times the cross-sectional area times the temperature gradient. So if we derive the expression of thermal conductivity, so what we get is actually negative dq over dt divided by a d theta over dx. So hence what we get is the definition for thermal conductivity, which is defined as the rate of heat flow per unit cross-sectional area per unit temperature gradient. So basically, the thermal conductivity is actually defined as the rate of heat flow per unit cross-sectional area and per unit temperature gradient. So this one should be at the subject, which is of materials per unit temperature gradient. So that's it for the definition of thermal conductivity. Okay, so let's move on to part 2. So in determining the thermal conductivity of a weak heat conductor, so the major problem is the poor heat conductor. Explain how can it be overcome. So basically we know that the insulator, which is mostly should be the insulator, which is the heat conductor. So what we need to do is basically is to modify that poor heat conductor so that we are able to determine the thermal conductivity of that heat conductor. So what we need to do is modify it until so that the thermal conductivity can be increased. So from here, what we need to do in order for the thermal conductivity to be increased, so so let me just find it out. Poor heat conductor, explain his. Alright, so what we need to modify is increase the cross-sectional area. Sectional area. So increase the cross-sectional area. So basically we know that the thermal resistance is actually equals to the L over Ka, which discussed from the previous parts. So basically this is R. So if we increase the cross-sectional area, so basically the resistance will be lower. So basically we need to do is increase the cross-sectional area so that the heat flow should be the rate of heat flow should be increased. So from this equation we can also see that if the cross-sectional area is increased, and hence, and I should use this one as the reference. So based on this equation, so ignore this equation. So based on this equation, if I increase my cross-sectional area, so what we get is actually the higher rate of heat flow. So higher rate of heat flow is able to enable us to find out what is the thermal conductivity of the materials. Okay, so this is the first way. So as for the second way, what we can do is actually use the thin layer of the materials. So thin layer of the materials enable the heat to be flow faster. This is because if the layer is thick, it means that the heat flow is actually, how should I describe this? Um, if the layer is very thick, it assumed to be the higher resistance which exists in the materials. And hence, what we need to do is actually use the thin layer of the materials so that the heat can flow through the conductor more easily. So this is two of the ways that we can determine the thermal conductivity of the poor conductor, heat conductor. Alright, so this is B. Okay, so let me just erase all this one. Okay, so this one as well. Alright, so let's just move on to part C. Okay. Oops. So here. So the wall of the house is made of bricks with a thickness of 20 cm. So basically our dx is actually 20 cm. So and has the area of 30 meter square. So this 20 cm I should convert it into the base form, which is times 10 to the power negative 2 meter. So in the afternoon, the outside temperature of the house can reach 38 degrees Celsius. So this considered to be theta 1, which is outside the house, which is 38 degrees Celsius. So in this case, what we use is actually in terms of theta. It's not necessary for us to convert it into the form of Kelvin. So this is 38 degrees Celsius, while the inside temperature is maintained. So this is theta 2, 18 degrees Celsius. In order to reduce heat loss, the contractor applied plaster with a thickness of, okay, so this is dx1 and this is dx2. So 15 millimeter, so 15 millimeter basically is times 10 to the power negative 3 meter. So on the inside surface of the wall of the house, so assuming that the outside and the inside temperature of the house are constant, so the outside and inside temperature of house are constant, so calculate the rate of heat flow through the wall without plaster. So initially there's only the wall here and there's no plaster. So what we get is actually, so the rate of heat flow. So the rate of heat flow is actually dq over dt equals to negative Ka d theta over dx. So so um so this should be the K1, uh, and the K2 is basically the plaster. Okay. So and the plaster. So there's something missing for the thermal conductivity. Alright, so let me check for a moment. Thermal conductivity of the brick is 0.84 N. So there's something missing. Oops. Okay, let me just modify for a second. So this one should be 4.0 times 10 to the power of -3 watts watt meter to the power of -1 K to the power of -3. Okay, so this is the thermal conductivity for the plaster. So initially, what we have is only the bricks and without the plaster. So this K1A, so this is the theta 2 minus theta 1. So this is our dx. So dx is actually 20 times 10 to the power -2. So, okay, if I expand this negative into inside, so what I get is theta 1 minus theta 2 divided by dx. So the thermal conductivity of the bricks is basically 0.4. So the cross-sectional area is 30. So the theta 1, what will be the theta 1? Okay, so theta 1 is 38 minus 18. So okay, so our dx for the bricks is actually 20 times 10 to the power -2. So this will be our final answer, which is 0.84, 30, 38 minus 18 divided by 20 times 10 to the power -2. So the final answer will be 2520. So this is in terms of joule per second, which is the power. Okay, so for the part 2, and let me zoom in it. So calculate the rate of heat flow through the wall with the plaster. So after that, the contractor is actually added the plaster. So what we need to know that if the plaster is added, so the heat is basically will not flow into inside will not flow into inner parts of the house. This is because the plaster actually is a insulator. So not I should not say that it's totally no heat will flow into the inner parts of the house, because the insulator is also able to conduct heat through the vibration of lattice atoms. So there's only a small amount of heat will flow into inside the house. So which means that the heat should I say there's a slightly heat loss to slightly heat loss will loss into the inner parts of the house. Okay, so what we need to do is actually calculate the rate of heat flow through the wall with the plaster. Okay, so basically dq over dt is actually equals to theta 1 minus theta 2 divided by the total resistance of the two materials. Okay, so what will be our theta 1? So this is 38 and this is 18. So 38 minus 18. So what I get is the, okay, so my first length is actually 20 times 10 to the power negative 2. So the thermal conductivity for me is, for the bricks, is actually 0.84. So the cross-sectional area is 30 plus the length of the plaster, the thickness of the plaster is 15 times 10 to the power negative 3. So the thermal conductivity of the plaster basically is 4 times 10 to the power negative 3. So cross-sectional area are the same. So this will be our final answer. So 38 minus 18 divided by 20 times 10 to the power negative 2 divide 0.84, 30 plus 15 times 10 to the power negative 3. So this is 4 times 10 to the power negative 3. So this is 30. So basically the rate of heat flow for the both bricks and the plaster is 150.45 joule per seconds. So this is how we calculate the rate of heat flow for two different materials. Alright, so just like so. So let's just move on to the next question. So calculate the interface temperature between the wall and the plaster. Okay, so let's just erase all this one. So the interface between the bricks and the temperature basically is the temperature which is in the middle of the two materials. Okay, so this is part 3. So since the rate of heat flow between the bricks and the plaster are the same, so I can say that dq over dt for the bricks is actually equals to dq over dt for the plaster. So negative ka d theta over dx equals to, so this is k1x and this is k2 a d theta over dx. So this can be cancelled and this one can be cancelled as well, and this is theta 1 and this is theta 2 minus theta 1 divided by dx1 equals to k2 theta, sorry, this one should be my interface temperature, which is theta 3. So theta 3 minus theta 1. So okay, so this is dx2. So this is k2, and okay, let me just erase all this one so that I have a bigger space. Alright, so let's just move on. So this one is 0.84, and theta 2 basically is the 18 minus theta 3 equals divided by dx1, and what will be our dx1 is basically equals to 20 times 10, and what will be the power times 10 to the power negative 2. So equals to the K2, and the K2 basically is 4 times 10 to the power negative 3. So theta 3 minus theta 1. So theta 1 will be 38 degrees Celsius. So the dx2, and what will be the dx2? 15 times 10 to the power negative 3. So what we have here is, okay, what we need to find is the interface temperature. Alright, so we need to do it step by step. So 0.84 divided by 20 times 10 to the power negative 2. So 4.2 times 18. So if I expand both of this into 18, so what I get is actually 75.8 minus 0.84. Not 0.84, sorry. So 0.84 divided by 20 times 10 to the power negative 2. So what I get is 4.2 theta 3. So what will be the another side? So this is 15 times 10 to the power negative 3. So this one will be the 4 over 15 theta 3 minus 4 over 15 times 38. So what I get is 152 over 15. So if possible, we should write this answer in the form of fraction, so that the final answer will be more accurate. Okay, so what I get for theta 3 basically is, so 4 over 15 plus 4.2. So okay, so this one is 67 over 15. So okay, 75.6 plus 152 over 15. So this is 1286 over 15. So this one can be cancelled, and theta 3 finally is 1286 over 67. So the final temperature will be, alright, so there's something missing here. So what will be the mistakes? So theta 18 minus theta 3. Okay, so theta 2 minus theta 1, and this is 18, okay. And this is 4 times 10 to the power negative 3, yes. And okay, so theta minus 38, is it 38? Yes. Okay, so what will be the mistakes here? So the answer should be 36.81, but the answer what I get is actually 19.19 degrees Celsius. And so, okay, what will be the mistakes? 75.6 plus 152 over 15. So 12x6 over 15. 4 over 15 plus 4.2. 67.15. Okay, so is it the other value where I got wrong? So this is 15, yes, and this is 20, yes. Okay. Alright, so give me a moment. Wait, let me check the answer again. Okay. Twelve is 0.2, 0.015. This is 30, 0.8. Okay. And let me recheck again whether which part is wrong. Zero point 0.84, 18 minus over 20 times 10 to the power negative 2. So 4 point times 10 to the power negative 3. It's over. Okay. So 15 times 10 to the power negative 3. So I wonder where is the mistakes here. And okay. Theta 1 minus theta 2. Alright. So this is the there's something there's a mistakes I found. Okay. So this one should be theta 1 and this one should be theta 2. So this one is theta 1 and this one is theta 2. Since the heat is flow from the outside into inside. Okay, so alright, so let me calculate again. So this one is 38 and this one is 18. Okay, so alright, so okay, let me recheck again. So 0.84 divided by 20 times 10 to the power negative 2 times 38. So times 38, what we get is 159.6 minus 4.2 theta 3. So this 4 times 10 to the power negative 3 divided by 15 times 10 to the power negative 3. So basically this is 4 over 15 theta 3. So this one should be multiplied by 18. So this is 24 over 5. So basically the theta 3, 4.2 plus 4 over 15. So this is 67 over 15. So basically what we get is actually the same thing, but is it correct? Plus 24 over 5, and this is 822 over 5, and final answer we get is 67 over 15. So yes, the final answer should be 36.81 degrees Celsius. So this is the final answer. So I think the mistakes is actually came from the calculation parts. So this one should how should I say that? This one theta 1 minus theta 3 should is also equals to theta 2 minus theta 3. So let me just check again. So this dq over dt is actually negative ka. So theta 2 minus theta 1. So this is x. Sorry, this one should be theta 3. So this is the dx1. And okay, so let me check again. So this is theta 1 and this is theta 3, and there's a mistakes, and I wonder why theta 2 minus theta 1 is not applicable, and it should be the same. So okay, never mind, I'll recheck again. So okay, so basically the general formula is actually from the outside into inside, which is theta 1 minus theta 2. So theta 1 minus theta 2 is actually from the hotter region to the colder region. So this is the main concept. Alright, so we have done for the question. Okay, so this is part C. Okay, so we have done for question 1. So let's just move on to question 2. Okay, let me drag it down. And this one shall be erased. Alright, so we have our question 2 here. So the rate of heat flow through a conductor of a cross-sectional area is actually given by dq over dt negative ka d theta over dx. So explain the meaning of the negative symbol in the equation above. Okay, so negative sign as we discussed is actually meant by the direction of heat flow in the decreasing temperature. So as I said, the heat flow is actually from the hotter region to the colder region. So this is the main concept. So this is number 2. At the end of the long metal rod of uniform cross-sectional area is heated, state the conditions so that the temperature gradient is constant along the rod. So there's an arrow here. So if the temperature gradient when the temperature gradient is constant along the rod, it means that the rate of heat flow is actually not rate of heat flow, sorry. So if the temperature gradient wish to be the constant, and hence the material should be the conductor the conductor must be perfectly insulated. So we talk about from the previous video, we said that when so let's say I have my road here. So this road is actually perfectly insulated. So this road at the end of the at two end of this road, we what we add is actually the object A and object B. So object A has the theta 1 and this has the theta 2. So basically the heat flow is actually from object A to object B. So within the process of the heat flow, the temperature at every point is actually varying. So the varying of the temperature at a certain time, the temperature will sorry, let me repeat again. So at the steady state, which is time t, the the difference in temperature is actually achieve the steady state. So what we need to do for the temperature gradient to be constant, so the conductor must achieve the steady state. So steady state basically it means that this is the temperature and this is the x. So steady state is the straight line for the graph of temperature against the distance. So basically from this graph we can say that the temperature at every point, the difference in temperature for every point are equal. So if the graph achieves the steady state, so what we get for the temperature gradient is actually a constant, d theta over dx, and this shall be the constant. Alright, so this is how the temperature gradient constant works, and let's just move on to the next part. Okay, oops. Alright, let me just drag it down. So let's move on to the part 3. So a refrigerator has wall of the thermal conductivity of 0.050 W M -1 K -1, and the thickness, so my thickness basically is 90 times 10 to the power -3 meters, and the effective cross-sectional area of 5.6 meter square. So the space in the refrigerator is required to maintain at the temperature of 25 degrees Celsius. So basically this is 25 degrees Celsius, less than the temperature outside. So calculate the minimum power of the refrigerator. So what we have here is actually dq over dt. So this is the this is Ka d negative Ka d theta over dx. So and the temperature less the space in the refrigerator is required to maintain at the temperature of 25. Alright, so the negative sign is actually can be neglected in this case. So thermal conductivity is 0.05 and cross-sectional area is 5.6. So d theta over dx, so the change in temperature, which is actually equals to 25 degree Celsius. So the change in temperature in the space of the refrigerator. So this is outside. So this is the space of the refrigerator until the inside. So between here, between outside to inside, the change in temperature is actually equals to 25 degrees Celsius. So what we have is so this change in X is actually equals to 90 times 10 to the power negative 3. So 0.05, 5.6, 25 divided by 90 times 10 to the power negative 3. So what we have here basically is 77.78, and this is watt. Okay, so this is the question number part 3 for number 2. Alright, so we have done for question number 2, and let's move on to question number 3. Okay, so let me just drag it down. So this is number 3. So metal rod P and Q has the same cross-sectional area of the length 80 and 40 respectively, are joined as shown in figure. So the thermal conductivity of the rod PQ are Kp and Kq respectively. So both rods are well insulated. So write an expression for the rate of heat flow in the rod. So basically rate of heat flow in the rod is dq over dt negative Ka d theta over dx. So this is the first answer. So state the two conditions for the expression to be valid. So okay, so write expression for the heat flow. Okay, state the condition of the expression in 1 to be valid. So basically it's actually similar to the question 2. So the rod must be perfectly insulated. So okay, and this is the first one. So steady state. So steady state, as we discussed from the previous parts, steady state must be attained. So steady state for the temperature, and what we have is what we will get is basically is the constant temperature gradient, and hence if we have the constant temperature gradient, and what we have for the last but not least is the constant rate of heat flow. Okay, so this is the second, and what will be the third part? So sketch a graph for the temperature gradient against the distance for the joint rods. So this, let us settle the first part first. Sketch a graph for the temperature gradient against the distance for the joint rods. So basically two rods has the different temperature gradient. So what we need to do is find out the temperature gradients. Okay, so I think I lost something here, which is the interface temperature. So let me check it out. Okay, so the interface temperature basically is equals to 25 degrees Celsius. So without the interface temperature, we are not able to find out the temperature gradient. Alright, so when the rods are the steady states, it means that the temperature gradient is actually a constant value, which is shows shows horizontal line in the graph. Okay, so let's do it. So for the first one, for the road P, so what we have here is the temperature gradient for road P. So what we have is theta 1 minus theta 3 divided by L. So my theta 1 shows 100 and this is 25, and so is it wait, let me check again. Alright, so this one should be negative because the temperature gradient is actually how should I set that is so let me check for a while. So sometimes this formula I also not sure about it. Okay. Alright, so the temperature gradient is actually includes the negative, which show the sign of decreasing temperature. So this one, so because usually what we do for the dq over dt is actually equals to negative Ka. So this one, what we do is basically is theta theta 2. So basically is generally is final minus the initial. So let's say the interface should be the so let's say the interface shall be our final for the root P for the final temperature. So minus the initial, and what we get is basically is and okay, so this is quite confusing. So let me check for a while. So I wonder why the negative should be included here. So let me check again about the formula. So sometimes this formula is quite confusing for me. Oh, okay, so I found it. Alright, so I get it. So basically from the previous video we talked about the graph of temperature. So the temperature basically is the decreasing graph, which is from the hotter region to the colder region. So what we get for this gradient is actually negative. So negative is equals to the negative temperature gradient. So that's why we need to add the negative in here. So basically the previous video has we have discussed about this. So the problem is sometimes I forget the formula, so my mistakes, sorry. So this one should be theta 3 minus theta 1 divided by L, and theta 3, what will be my theta 3? So 25 minus 100. So this is 80 times 10 to the power negative 2, and okay, let me just drag it down. So 25 minus 100 divided by 80 times 10 to the power negative 2. So what I get is negative 93.75. So okay, yeah, this is the temperature gradient for root P. So I wonder what will be the SI units. So dq over dt negative Ka d theta over dx. So d theta over dx. So this is dq over dt Ka. So okay, so I've got the SI units. So SI unit for the temperature gradient basically, which is from the formula, which is d theta over dx equals to, okay, let me drag for slightly a bit to the right side, Km negative 1. Okay, so this is the temperature gradient for root P. So what about root Q? So root Q basically is so what we have here is negative d theta over dx, of course. So this is negative 2 minus negative 3. So is it correct? So let me just... Alright, so theta 1 minus theta 3. Okay, so this one shall be... So this one shall be theta 3 minus theta 1. My mistake again. So this one should be 2 and this one should be 1. And okay, the negative expand. So this one is theta 1 minus theta 3. So this one shall be L2 and theta 1 basically is 0 minus theta 3. So theta 3 basically is 25 and L2, so the length for root Q is 40 cm. Alright, so this one negative 25 over 40 times 10 to the power negative 2. So basically is 62.5 K per meter. Okay, so sometimes this formula is quite confusing. So what we need to do is to be more careful about this question. So this let me recheck again whether it is correct. So this one shall be my T1. So let's say this is root P. So this one is for the addition, and this one should be the theta 3 and 0, and this one is the change in x. And so y2 minus y1 over x2 minus x1. So right, so minus the theta 3. So y2, what will be my y2? So my y2 is negative 1 minus y1. So y1 is negative 3 and x2. So y1 is the y2 is this one, and basically x2 is this one, 0 minus change in x. So basically the theta 3 is the change in theta 3 is actually the initial minus the change in theta. So this one shall be negative and this one can be cancelled. And okay, so there's a mistake. And how could it be? And this one should be 2 and this one should be negative 1. Alright, oh yeah, I saw it. So this one shall be negative, negative, positive. So what we get is actually negative d theta over dx. So this is the actual formula. Alright, so yeah, the derivation has shown the temperature gradient is actually consists of negative sign. So the negative sign for the rate of heat flow is actually came from here. Okay, so we have done for question 3. So let's just move on to question 4. Is it? Yeah. Oh, there's one more question. So I miss it. So this one is question 4. So determine the value of Kp over Kq. So what we need to do, is actually equals the both side of the rate of heat flow. So P is actually equals to Q. So this is negative Kp A d theta over dx equals to negative Kq A d theta over dx. So since the cross-sectional area are the same, so we can cancel out each other. So Kp over Kq, so this one also can be cancelled. Kp over Kq, and this one is P and this one is Q. So this is theta Q over d theta over dx P. So what we need to do is only substitute negative 93.75, so divided by negative 62.5. So the ratio actually indicates sorry, and there's a mistake again. So 62.5, 97.5. So is it? Oh, I saw it. Okay, so this is basically is the temperature of rod Q. So since the thermal conductivity is inversely proportional to the temperature gradient, so this is 62.5 and this one basically is 93.75, and what I get for this answer is 0.67. This shall be the final answer. Alright, so we have done for question 3. Okay, let me just erase here. Oops, okay. Let me erase this one as well. Alright, so let's just move on to the last question. So let me zoom it out for a bit. So this is question 4. Sorry. So a silver rod and the iron rod has the same mass, have the density of. So let me check the value whether it is correct. So 10500 and 7860. Okay, correct. So the silver has the density of. So this question is actually a popular question for the STPM. So this is meter cube. So this iron rod, so basically iron rod has the density of 7860 kg per meter cube and respectively. So both rods conduct the same amount of heat in 1 second when my dt basically is 1 second. So when the difference in the temperature between the two rods are the same, so this shall be the difference in temperature. This shall be our keywords. So if the thermal conductivity of the silver rod, so we have the thermal conductivity for the silver rod, which is 420 watt per meter. Okay, so and the iron 79. Okay, so what is the ratio of the radius of the silver rod to the radius of the iron rod? So basically the question asks for the silver to the iron. So this is what we need to find. Alright, so let us just begin with this. So basically what we know for the formula of the densities is actually the m over v. So the density for the silver is actually equals to the mass of the silver divided by the volume of the silver. Okay, so this is the alright, so this one should be the formula, and this one is 10500, and this is the mass of silver, and this shall be the volume of silver. Okay, so let me just drag it down. So the mass of silver basically is the volume times times the 10500. Okay, so this is the mass of silver. So this also same goes to the mass of iron. So I can conclude that by the mass of iron, my mass of the iron basically is the volume of the iron times the density of the iron, which is 7860. So the question does mention about the mass. So the mass of the silver rod is equal to the iron rods. So the mass of silver is equals to the mass of iron. So this is the V. Okay, so let me just the rods. Okay, so V, the volume of silver, 00, so equal to the mass of the iron. So basically, we know that how should I say it? So the rod, both rod, we consider both rod as the cylindrical shape. So the volume for the cylinder is actually pi r square Ag, and this one shall be the height. So the height basically is our thickness of the rods. So this one is okay. So let me write it more properly. So this one is 10500, and this one is pi r square for the iron. So this one is the length of the iron. So this one is 7860. So both pi can be cancelled, and what we have is so let me just move this arrange in orderly. So what I have is okay, LFE over LAG. So this can be moved to this side. Or I shall move this one to the other side. So since I will substitute into another formula. Okay, so wait a minute. Okay, so I just remain as this form. Okay, so this is the first information. So as for since both rods are attached to each other, so I can conclude that the rate of heat flow throughout the both rods are the same. dq over dt, and this is for iron. So Ka d theta over dx, and this one is the Ka and d, and this one should be the silver, and this one shall be the iron. Alright, so okay, so let me just find out. Okay. Oh, okay. Okay, so since the heat flow is in the 1 second, so this can be cancelled. Both rods are the 1 second, is it correct? So, okay, both rods conduct the same amount of heat in 1 second. Okay, so the dt proves us that the dt is actually equals to 1. Alright, so then what will be our heat flow? So the heat flow basically is, okay, let me think about it. So how can, okay, so let me think a moment. So this question is actually quite um, high high scale thinking. So I need some times to think about it. So then what will be the, so give me a moment here. Okay, so all right. Okay. All right. So did I lose something in the questions? Oh, I saw something. So just now I just highlight the sentence here. So the difference in temperature between the two rods are the same. Okay. So let not use this formula. So same, the heat flow in the silver is equal to the heat flow in iron. So this one shall be the Ka, and this one is the cross-sectional area of the silver, and this one is the temperature gradient. So minus KFE AFE d theta over dx, and this one also, oops, and this one should be the iron. Okay, so since the difference in temperature for the both rods are the same, so what we can do is basically cancel both of this. Alright, so what we have here will be the okay. So let me just observe for a second. Alright, so I got it. Okay, so this dx is actually equals to the length. So what I can do is Fe over L over Ag expressed in terms of this ratio, Ag Rfe square times 10500 divided by 7860. Alright, so this one shall be the answer. So this can be cancel, and let me just drag it down. So this is the pi r square. So our h is Ag. So the KFE. So the cross-sectional area for the iron is pi r square L, and this one is the iron. Iron. So L is the iron, the length of the rod, of course. So this one is dx. Okay, so there's something wrong again. Okay, let me just observe for a while. So let me think for a while whether there's mistakes. Okay, so it's actually quite confusing for this one. Alright. Oh, there's a mistake here. This one shall be the cross-sectional area instead of volume. So this one, there's no L here. Okay, so this one, okay. So this one should be the LAG, and this one should be the LFE. So what we need to do is drag the FE over LAG. So KFE, so pi can be cancelled, and KFE R square Fe divided by the KAG R square AG. So this shall be our final answer. Okay, so alright, so this one, so let me think for a while. R square, okay. Okay, so what we need to do is just substitute this one, square over R Fe square. So substitute the length, which is 105007860 divided by the K equals to KFE R square Fe over the KAG R square AG. Okay, so finally this one is the Ag over Fe. So this is the power of 4, and this is the K and KFE over the KAG divided by times the 7x60 divided by 10500. Okay, so what we get finally, so the thermal conductivity of the iron is, okay, so 79 divided by the silver thermal conductivity of silver is 420. So this one is 7860. Okay. So this shall be our final answer. Ag and RFE 79 over 420. So okay, this one is answer, and what we get is 0.61613. So this shall be our final answer. Okay, so as for the question 4, it's actually quite long, so we need to do it step by step. So what we have to consider and be careful is the keyword which given by the sentence, which is quite important. So if there is the keywords given by the question, we need to list out one by one so that we are able to find out what the question asks for. And this question is actually the STPM question before the semester. So this question is actually quite hard for some students. So even for me, it's actually quite hard as well. So what we need to do is um, think it slowly and find out the solution. So that's it for the solution of this question. Alright, so we have done for all the 4 questions for this chapter. So we have done, and I think we stop here. So if there's any question need to be asked, and please comment below this video, and I'll see you next time in the new chapter. So thank you. Bye.